Today I wanted to take a second look at lesson 6-4, which was on exponential growth and decay. You all have prior experience with exponential functions. They're things you should have already been familiar with even in an Algebra 2 course, and of course in pre-calculus we look at these sorts of functions as well. In AP Calculus we look at them again. However, in this particular case we're going to be focusing on them as a particular kind of solution to differential equations. We started the chapter introducing differential equations, and this is a particular very important kind of differential equation. We'd like to see how this comes about, and in doing so we also get to explore a specific technique for solving many special kinds of differential equations. I know we've already discussed this in class, but there were several questions on things, and I thought I would try to present things again to you in another way that would give you some different perspective on matters. So let's begin by just describing separable differential equations once again. If you think about a differential equation, what it really is it's information about the derivative of a particular function. The types of differential equations we have seen so far have been something along the lines of the first derivative of some function y is equal to, and over here, literally over here, we can put anything we want. Within reason, obviously we need to put variables over here. We can't put anything that's nonsensical over here. But in terms of functions, in terms of the way that we write things out, anything we want can go over here. And we can describe this then as simply saying this tells us something about the derivative of the function y. So this function y, we have information about its derivative, and being good calculus students, knowing our derivatives, we can work with antiderivatives to work backwards. Okay? So the way in which we have typically solved these problems is we solve by knowing the antiderivative. We have had other techniques that we have used, and I don't want to sell those short, but most of those were not exact. So slope fields are a way for us to get a graphical, visual image of what the solutions to a particular differential equation may look like. Euler's method gives us an opportunity to look at things in terms of a numerical approximation to the solution. But if we really want to solve a differential equation, one of the big issues is that we need to know the antiderivative, and that is what a lot of our focus on this particular chapter has been, is working with these antiderivatives. Well, that's a problem, because if we have this differential equation, here where we have anything we want over here, we run into some serious difficulties. Our knowledge of differential equations is pretty limited. It's limited by our antiderivatives that we know. We know very few antiderivatives. In terms of writing something here, we have to be very careful if we want to be able to actually do the integrating, if we actually want to find the solution. So separable differential equations are ones in which we have dy dx is not equal to anything we want, but dy dx is made up of two pieces. Dy dx has to be made up of two pieces, one of which is a function that can be written in terms of y, and the other is a function that can be written in terms of x. What this really means for us is that the x and y dependence can be factored out, or can be factored into two separate pieces, or can be separated. We can sort this out into a piece of our derivative that depends on x and a piece of our derivative that depends on y. This is a separable differential equation. When this occurs, when we are able to separate out the x and y dependence into two separate factors, into two separate pieces, we say that the differential equation is separable. And this is good news for us when we go to attempt to solve these differential equations. We actually can do something about that. So let's take a look at some examples. We won't go through and solve all of these, but let's look at a few examples of differential equations that may or may not be separable. So for our first example, let's look at dy dx is simply equal to x. This is a very familiar, straightforward differential equation. It simply says that the derivative of a function, the slope of a line, is simply equal to the x-coordinate. We've worked with this with slope fields. We've looked at this in several different ways. Is this a separable equation? Is this a separable equation? This is a separable equation because we can write this derivative, we can write this differential equation as a part that has an x dependence and a part that has a y dependence. The x dependence here is just x, and the y dependence is trivial. There's no y coordinate here, there's no variable here, y, that we need to factor out. So this is separable. It's separable in sort of a trivial way, but it's good to see that many of the differential equations we already know how to solve are equations that are separable, and we have lots of techniques for solving these. Well, let's take a look at another example here. What about the expression dy dx is equal to x squared y? Is this a separable differential equation? Can we write this as some function of x and some function of y? Certainly, we can think about the x dependence and the y dependence separately. So this also turns out to be a separable equation. And of course, we can look at much more complicated examples. And it's important to note that just because an equation is separable does not mean we can necessarily solve it. We still need to know antiderivatives, as we'll see later on. But it is a first step that helps us to classify certain differential equations. What about this equation? The derivative of y is equal to x plus y. Is this a separable equation? Can we separate this out into a function dependent only on x and a function only dependent on y, the product of those two things? Can we do that here? We actually can't. This is not a separable differential equation. We cannot write this as some function of x times some function of y. And if you think you can, if you think you see how this works, I think you should go for it. Give it a try. See what you come up with. Play around with it and convince yourself that there's no way to do this. There's no way to write this as a function of x times a function of y. That does not mean that we can't solve this differential equation. But what it means is that we have to think of other techniques. Perhaps here we could find some sort of antiderivative that may work, or some other technique, but the technique we're going to see today would not work in a problem that is not separable. Well, let's take a look at a separable differential equation, and let's see the technique for actually solving this differential equation. So let's take a look at the example dy dx is equal to x squared over y. This is a separable differential equation because I can write this as a function of x and a function of y multiplied together. So this is indeed a separable equation. And the technique for solving a separable differential equation, or at least getting it into a form which we can start to look for solutions, is to move the x dependence on one side and the y dependence on the other. So we want to sort of further separate the x and y dependence so that they're each on opposite sides of the equation. So we move all x dependence, including the differential dx, move all x dependence and y dependence to opposite sides. This is somewhat akin to what we've been doing when we have been using u substitution to set up and try to solve integrals. One of the things we do there is we let u equal some function of x. We take derivatives and then we separate those derivatives, so we have u on one side, x on another, and that's what allows us to completely change variables in our equation. The same sort of thing is going on here, where we would like to be able to separate things. So with our equation here, dy dx is equal to x squared divided by y, what we would like to do is move the y dependence over to the left. So I would multiply here both sides by y. That will cancel out the y's here, leaving me with y dy dx is equal to x squared, and then we would move the dx dependence over, multiplying by dx on both sides, and now we have separated our separable differential equation. I end up with y dy is equal to x squared dx. Now if you think about this, these are small differential changes. These are small changes to functions. And what this tells us is how those small changes accumulate, how those small changes affect one another. And what we're going to do is we're going to add up all of these small changes. We're going to integrate the left-hand side and the right-hand side. Integration, again, just like derivatives or anything else, is an operation, and we're allowed to perform that operation on both sides of an equation, just like subtracting the same thing from both sides when you're solving an algebra problem. We're allowed to integrate both sides, and according to the laws of algebra and the laws of calculus, the left and the right-hand sides will remain the same. One of the stumbling blocks I think that people have been having in this particular work is integrating y with respect to dy. We sort of hold a special place in our hearts for y. Y is supposed to be a variable that depends on x. But in this particular case, we treat y as just purely a variable. So we think about this simply as the integral of y dy, and we treat y as though it were x. So we say what function, what object has a derivative that's equal to y. So what we need to do here is simply integrate. And the integration of any variable with respect to that variable is simply going to be 1/2 that variable squared, or in this particular case 1/2 y squared plus a constant. I'm going to label this constant 1, because we're going to have several constants as we go through these problems today, and we'll talk a little bit about keeping track of them and how much we really have to worry about all of these constants. But the left-hand side is 1/2 y squared plus a constant. If you take the derivative of that with respect to y, you simply end up with y. So this is the correct antiderivative here. On the right-hand side, we have the integral of x squared with respect to dx, and of course the integral here is simply going to be 1/3 x cubed plus a constant. And we'll label this constant 2, so again we can keep track of these constants. We don't know what these constants are, and unless we're given an initial value problem or we're given limits of integration, these constants are things that could be any number, right? They're not fixed until we decide on a particular initial value or a particular value that our line or our solution passes through. Once we do that, we fix that constant. But until then, it's available to be any value. In fact, it's good to think of this constant as representing any value. Think about those vertical shifts, right? Think about that solution and the vertical shifts. Very, very evident, very clear to see when we start to talk about slope fields, and we can see the layer upon layer of different functions that are solutions there. Well, one of the things we like to do typically is solve an equation like this for y. We like to determine what the function is. So here with the y squared, we have to be careful. We're going to go ahead and do a solution here. One of the first things I'll do is I'll move my c1 over here. So we'll subtract c1 and start to move things over to the other side. That leaves me with 1/2 y squared is equal to 1/3 x cubed plus c2 minus c1. And then I can go through and I can multiply both sides by 2, and we end up with y squared is equal to 2/3 x cubed plus 2 times c2 minus c1.